testing mu, the mean of a population. Case 1. X, the population random variable, is normally distributed. Sigma squared is known, and in this case n, the sample size, can be large or small. Again, okay, we're going to talk about case 1 first, where X, the population random variable, is normally distributed. We know the value of sigma squared, and n, in this case, the size of the random sample, can be large or small. So let's look at an example, read through the question, and then work through the problem. When clients visit a certain a certain firm of solicitors, the duration of appointments in minutes may be modeled by a normal distribution with mean 50 and standard deviation 5.3. Okay. Following the appointment of 2 new solicitors, the mean duration of a random sample of 15 appointments, so n is 15, and the mean duration, we have got x bar equals 54.2. Great. Assuming that the standard deviation is still 5.3 minutes at the 1% significance level, so alpha equals 0.01, we are asked to test whether the mean duration of appointments has increased. Okay, important word. Let's look at the solution. X represents the duration of appointments. Again, X represents the duration of appointments, and we are told that X is normal with a mean of 50 and a variance of 5.3 squared. Good. So just to remind you, we are dealing with a normal distribution and our variance is known. Now let's go ahead and set up our hypotheses. H naught, mu equals to 50. Where do we get this from? From the first paragraph. Okay. Now H1, we are testing mu bigger than 50 because we are trying to test whether the mean duration has increased. So mu bigger than 50. So we know we are dealing with a right tail test. Okay. So let's draw a line here. A right tail test. All our rejection probability is in the right tail. So the rejection probability is 0.01. Now, remember we are dealing with a normal distribution here, and let's go ahead and draw a little picture. Now, I have placed all the rejection probability in the right tail, 0.01. Now, the value of Z, okay, is 2.326. This is the critical value of Z. Now we know the sample size is 15. We know X bar, the sample mean, is 54.2. Let's go ahead and work out Z, the test statistic. X bar minus mu over sigma over square root of n. You plug in all the values. Okay, plug in all the values, and you'll get a value of Z which is 3.069. Now 3.069 falls in the rejection region. So that's what I've written here. Okay, 3.069, the Z value, falls in the rejection region. Therefore, we have to reject H naught, which means there is evidence that the mean duration has increased. Okay, now let's look at the next example. Let's read it. A machine fills cans with soft drinks so that the contents have a nominal volume of 350 ml. Over a period of time, it is found that the volume of liquid in the cans follows a normal distribution, important, with a mean of 335 and standard deviation of 3. Good. A setting on the machine is altered, following which the operator suspects that the mean volume discharged by the machine has decreased. Okay, so important word, decreased. Now he takes a random sample of 50 cans, n equals to 50, and finds that the mean volume of liquid is 334.6. So X bar is 334.6. We are asked to carry out a hypothesis test at the 5% significance level. So we know alpha is 0.05. We are asked to test whether the mean volume has decreased. Assume that the standard deviation is still 3. Let's look at the solution. X represents the volume of liquid. We are told that X is normal with a mean of 335 and a variance of 3 squared. So define the hypothesis. H naught, mu equals to 335 that we get from the first paragraph, the number here. And remember, we are testing whether the mean volume has decreased. So we have H1, the alternative hypothesis, mu less than. Now, let's go ahead and draw a little picture of our normal distribution. Remember, this is mu less than, so it's a left tail test. So a left tail test will place all the rejection probability in the left tail. So that's what you see here, 0.05 in the left tail. Now look up this value in your normal tables. The critical value of Z is negative 1.645. So next step, go ahead and work out the Z value. X bar minus mu over sigma over square root of n. Plug in all the numbers. 334.6 minus 335 divided by 3 over the square root of 50, and you will get a value of Z negative 0.943. Let's draw the critical region again. Okay, the normal curve, and we have our 0.05, and this value here is negative 1.645. Okay, the Z value that we calculated, take note, sometimes I write it as ZC, yeah? That means Z calculated. The Z calculated, we found the value to be negative 0.943, and 0.943, I'll repeat, negative 0.943 is here. Okay, it does not lie in the critical region. Again, the Z calculated, negative 0.943, does not lie in the critical region, so do not reject H naught. Therefore, there is no evidence of a decrease. Good. Let's look at our next example. Let's read it carefully. Okay. An athlete finds that her times for running a race are normally distributed with mean 10.75 and standard deviation 0.05. Good. She trains intensively for a week and then records her time in the next 6 races. Her times are given. Okay, 1, 2, 3, 4, 5, 6 values are given. So that's all here. And is there evidence at the 5% level that training intensively has improved her times? So be careful about this. When you improve on your time, your mu is less than. Okay, when you improve, that means you take less time to run your race. Okay, let's look at the solution. X represents the times for running a race, and we are told that X is normal with a mean of 10.75 and a variance of 0.05 squared. Now we have taken 6 values, so n equals to 6. We don't have X bar, but we can work it out. Yeah? So X bar equals to summation X over 6, add up all the 6 values of X that you see here, divide by 6, you will get 10.712. So we are testing whether training has improved her time. So let's set up the hypothesis. H naught, mu equals to 10.75, that's from here, and H1, the alternative hypothesis, mu less than 10.75. Okay, now since this is a left tail test, we will place all the rejection probability of 0.05 in the left tail. the z value from the tables is negative 1.645. Now we have to go and work out z calculated. Yeah. Now z calculated, you know, x bar minus mu over sigma over square root of n. Plug in all the numbers that we have, and you'll get a value of negative 1.862. Now negative 1.862 is here. Okay, negative 1.862. It falls in the rejection region. Therefore, we have to reject H0. So there's evidence that training has improved her times. Let's do a two-tailed test. We are given x is normal with a mean of 42 and a variance of 15.7 squared. We are told n equals to 3. We are given three values of x: x1 27, x2 35, and x3 43. We are told alpha is 10%, so alpha equals to 0.1. We are asked to test if the mean is different from 42. So let's follow the solution. N equals to 3, so we can work out the value of x bar. Add the three values up and divide by 3. You will get x bar equals 35. Set up the hypothesis. H0 mu equals to 42. H1, remember we are testing if the mean is different from 42, so H1 mu is not equals to 42. So this is a two-tailed test. So in the left tail we have a probability of 0.05, which is alpha over 2. Okay, alpha over 2 is 0.05. So in the left tail we have a rejection probability of 0.05. In the right tail we have the same value of 0.05. Okay, now we know the two values, negative 1.645 and positive 1.645. Now what's left? We have to work out z calculated, which is x bar minus mu over sigma over square root of n. Plug in all the values. 35 minus 42, sigma we know is 15.7 divided by the square root of 3. You work it out, you will get negative 0.772, and that is somewhere here. So z calculated does not fall in the critical region, therefore do not reject H0.